Welcome to the AICE Chemistry lecture series. In this video, we're going to start the chapter 9, which covers rates of reaction. This is a pretty small chapter, but it's an important one because it connects to thermodynamics, it connects to equilibrium, and basically to everything else we have done in physical chemistry. This is also the last video which covers physical chemistry, as chapter 10 is where we're going to start inorganic chemistry. So without further ado, let's get started with chapter 9. Chapter 9 has 4 main sections. We're going to look at first rate of reaction, what it is, how do we calculate it and measure it. We're then going to see how concentration affects that rate of the reaction. In section 3, we'll look at how temperature also affects the rate of the reaction. And finally, in section 4, we're going to look at the definition of catalysts and the different types of catalysts. So let's get started. Now there is one practical for this chapter, which is the rate of reaction practical, where we essentially do an experiment where we measure the rate. And we'll do that later in the class. But let's start with section 1. Section 1 is going to cover the basics. What is the rate of reaction? How do we calculate it? How do we measure it? And so on. So reaction kinetics. Reaction kinetics are the study of rate of chemical reactions. The rate of a reaction can be defined essentially as the change in amount of reactant or product concentration over a unit of time. So reaction kinetics in essence is just the chemistry of how quickly do reactions happen and why. And we measure the speed or how quickly a reaction happens by the rate. Now, change in amount of reactant or product is usually going to be measured in units of concentration. So the units for the change in amount of reactant or product are going to be in mole per cubic decimeter for those reactants or those product concentrations, where we are going to divide that by the amount of time that rate takes, the change in concentration takes, which is usually going to be measured in seconds. Now, for some much slower reactions, the time could be measured in minutes or even maybe hours, but for most reactions, especially those we're going to do in practicals and in AICE chemistry, the time is going to be measured in seconds. Because the change in amount of reactant is going to be a measurement of concentration, and that's going to be in moles per cubic decimeter, or moles dm to the negative 3, and time is going to be measured in seconds, that leaves us with, let me actually do it this way. That's going to leave us with most of the rates being measured in units of mole dm to the negative 3 s to the negative 1, or moles per cubic decimeter divided by seconds. Because remember that this is the same as saying moles divided by dm cubed times s. So it's the amount of change in concentration, moles per cubic decimeter, per unit of time or seconds. The stoichiometry of the reaction is not going to give us any information as far as how that rate is going to change. The stoichiometry of the reaction can give us information as to how the rates compare between different reactants or different products, but not about the rate itself for the reaction. Reaction kinetics uses a lot of experimental data in order to calculate those rates. By following the concentrations of a chosen product or reactant, we can see how quickly those concentrations happen if we time them. So essentially, all of reaction kinetics is not going to depend on stoichiometry or the chemical formula or the chemical equation for the reaction. It's going to depend on data from labs, on calculations. Essentially, we're going to grab a reaction, we're going to carry it out, and we're going to see how the concentration of a specific reactant or product changes over a specific period of time. And we do this in the lab. It is practical data, experimental data. We do not do this with theory. We cannot tell anything about the speed of a reaction just by looking at the chemical equation. So we'll move forward. There's a few experimental methods that we can use in order to study reaction kinetics or in order to study the rate of a reaction. So essentially, what differentiates these two methods or these two different types of method is that we can look at how the rate of a reaction changes over a period of time. So we can live or continuously measure that change, or we can do so in individual points in time. So we can carry out a reaction and then a specific amount of time, 1 minute, every 2 minutes, every 3 minutes, see how those concentrations have changed. So we call these experimental methods either sampling methods or continuous methods. A sampling method essentially involves taking a small sample of the reaction mixture at various points in time and then quenching them for the analysis. Now, that analysis can vary. Usually we'll use titration for concentrations, something that you should be familiar with by now. We have done 2 different titration labs. And then the term quenching essentially means cooling down a sample by putting it on ice to slow down or stop the reaction. So essentially, what we'll do is that we'll carry out a reaction, and every 1 minute, we'll take a small sample from the reaction and we'll put it on ice. And then once the reaction has cooled down and it has slowed down enough that we know it's not happening anymore, we'll carry out a titration to calculate the concentration of that particular reactant or product at that particular point in time. So this sampling method has obviously a few flaws, mainly in that we're not continuously monitoring that reaction. And the quenching can fail. If we fail to cool down the sample to a low enough temperature that the reaction keeps happening, the concentration we're going to get from the titration is going to be wrong because the reaction wasn't stopped appropriately or it wasn't slowed down enough to the point that it actually changed a lot of its concentration. So in order to circumvent that, we can also use what is called a continuous measurement experiment. In a continuous measurement experiment, it's going to involve some kind of tool like a electrode or a few other things that we're going to look at in a second to continuously measure the concentration of the reactant or products in real time. So whereas this first sample will require us to put a bunch of data points together and draw a line of best fit, with the continuous measurement method, because we're continuously measuring those concentrations in real time, we can make an actual graph of the concentration changes instead of plotting a bunch of lines and looking at the line of best fit. Now, some continuous measurement methods include things like colorimetry, which involves using a machine that looks at the color of a color solution and how it changes over time. So essentially, if the concentration of something like copper sulfate decreased, a solution will get less blue because copper sulfate is blue. We can also use a conductivity probe to measure how conductive a solution is. If we have something like ions being measured, because ions conduct electricity, or we can use something like the gas volume or pressure measurements from a pressure or gas volume probe. If we're working with gases. So this is just 3 different ways in which a continuous measure can work. Now, you might be asked about these, especially quenching is a key word for things like practical exams in paper 3. But for the most part, in paper 2, you're not going to be asked about the methodology like you're looking at here, but we're going to be asked about the data and how to look at the data and how to process the data and do mathematics with it. So let's look at those points here in section 1. So the rate of a reaction can be measured by looking at one of the reactants or products, right? Now, we're not going to look at every reactant and every product in a reaction because that's too many things, but we're going to focus on one reactant or one product and their concentration over time. The rate is going to be dependent on the concentration of the reactants. Why? When we have a chemical reaction, and we're going to draw here a generic chemical reaction. We have a reactant turning into a product, right? Let's not go into specifics, just reactants and products. So what happens? As the reaction proceeds, the reactant gets used up and the products get made. So the concentration of the reactants over time is going to decrease, whereas the concentration of the products over time, and remember brackets mean concentration in chemistry, is going to increase. So as the reaction proceeds, reactant concentration goes down, product concentration goes up. The reaction depends on the reactant concentration, because as the reactants crash into each other, that's what's causing the reaction. So the reactants decreasing in concentration means that the reaction slows down. As a reaction proceeds, the concentration of the reactants decrease, and so does the rate of the reaction. So let's look at a particular reaction to look at how that works. So let's talk about this reaction. Cyclopropane, breaks down into propene. I'm not going to go into the specifics of the chemicals because we haven't covered organic chemistry yet, but let's keep the names here. So cyclopropane breaks down into propene. So propene is a product and cyclopropane is a reactant. That means that over the lifetime of this reaction, the concentration of the cyclopropene, we'll just call that cyclo here, is going to decrease, whereas the concentration of the propene is going to increase. So that's how reactions work. Reactants get used up, they create products, right? In this case, cyclopropane gets used up and propene is made. And we can see that here. If we look at the data table we have for this reaction, at 0 minutes, we had 1.5 moles per cubic decimeter of cyclopropane and 0 of propene. So no propene have been made yet. After 5 minutes of this reaction, the concentration of cyclopropane went from 1.5 to 1.23, meaning that it decreased, so we're going to put a negative here, by roughly 0.27 moles per cubic decimeter. On the other hand, if we look at the concentration of propene, because it's a 1-to-1 ratio, the concentration of propene went up by 0.27 moles per cubic decimeter. So the concentration of the cyclopropane as this reaction goes on, we can see it keeps decreasing from 1.23 to C1 to then to 0.82, 0.67, so on and so forth, whereas the concentration of propene increases. Well, let's say we focus on the propene. So let's say we are going to focus here on the product to talk about the rate of the reaction, because we could look at either the reactant or the product. But let's say we talk about the product. That's what this graph over here is. This is a graph of the concentration of propene versus time. Essentially, we're looking at how does the concentration of propene change over the length of this reaction in minutes. So we can see here that the reaction is going to start at 0. Actually, let me use something different here. The reaction is going to start at 0 because we had 0 propene concentration at first. And then you can see that over the course of this reaction, as time proceeds, the concentration of propene increases. Every data point has a higher concentration. Now this, because we have data points, would be an example of sampling techniques, where we're sampling every few minutes, in this case every 5 minutes, to get an idea of concentrations. But notice that this is not a straight line. This is a sloping line. It's sloping down, right? The slope of this line is changing over time. Why? what is the slope of this line? If you remember from math, basic math, slopes are rise over run, right? Or y-axis over x-axis changes. Well, here our y-axis is the concentration of propene, whereas our x-axis is time. So the slope of this line is concentration of propene over time, which is the rate of the reaction, because we just saw that rate is concentration of a chemical, either reactant or product, over time. That means the slope of a line, of a graph, of concentration versus time is the rate of the graph. And as you can see here, as the reaction proceeds, the rate decreases, the slope decreases. We have here at the beginning, let me change colors, we have a very steep line. So the slope here at the beginning is very steep, whereas towards the end here, the slope is a lot flatter. And that's because as the reaction proceeds, the rate of the reaction slows down. Why does the rate slow down? Because the concentration of the reactant decreases and rate is dependent on the concentration of the reactant. So we can see that in this graph. This graph shows us concentration versus time. That means that the slope of it is the rate of the reaction. And we can literally see in this graph physically how the slope or the rate of this reaction decreases over time. So let's keep going here. So that's the rate and concentration. This is how we will use the experimental data, which is what this chart is, in order to get graphical data that we can visually see and show us the rate of the reaction. So let's talk about the data we can get from this graph. The first set of data is what we call the average rate of reaction. Now, the average rate of reaction is something that we measure for a reaction as a whole over a specific period of time by essentially using the slope formula. The slope formula, if you remember again from something, I think it's geometry or algebra 1, is rise over run, or y over x, right? And that's what we just saw in the previous slide. Here, rate is equal to delta reactant concentration. So the change, remember, delta in chemistry means change. So the change in reactant concentration over the change in time. Well, if you remember, because the y-axis is the reactant concentration, or actually the product concentration here, but we can use either a reactant or product, that's going to be y, so change in y over, because the time is the x-axis, change in y over change in x. Or y final minus y initial over x final minus x initial. So we can get the average rate of a reaction by picking any 2 points on the graph of concentration versus time for a specific reactant or product, and then plugging them into this equation to get the changes in the y's of the points versus the changes of the x's. It's essentially the same as calculating slope in math, but we're calculating the slope of a specific graph, which happens to be the rate of the reaction. This measured method, however, is very flawed because the graph of concentration versus time is not linear. If this was a linear graph, this would work great because it doesn't matter at what point on the graph you choose, the slope is always going to be the same. But because the line decreases in slope, because the line is curved, their different points will give us different rates for that reaction. So it doesn't matter whether we use these 2 points or these 2 points right here, we are going to get a different slope, average slope here than we do up here. And that's because the data points are going to be different because the slope of the reaction, the rate of the reaction, changes over time. So if we were to do this, for example, if I choose 2 points, I have 0, 0 here at the beginning, the origin, and then the first point that I graphed here was 5, 0.27, so 5 minutes, and then the concentration was 0.27. So if I do YF minus YI, so YF is the final Y, the second Y is 0.27, the first Y is 0, so 0.27 minus 0, and then XF, the final X, which is the X of the second point, which is 5, minus the X for the first point, which is 0, 5 minus 0, so 27 over 5, it gives me 0.054. So the rate here in this area of the graph, the average rate, is 0.054 moles per cubic decimeter per second. What this is telling us is that the concentration of propene at this point in the graph here is going to increase by 0.054 moles per cubic decimeter for every second the reaction is allowed to happen. But as we know, if I were to do the exact same math up here with these 2 points, that will be a much smaller rate because the reaction up here has slowed down since the concentration of the reactants are smaller. So that's the average rate of a reaction that we can get from data points on the graph. But again, this is flawed and not used that often. So let's look at a different way of looking at this. We can also calculate what is called the instantaneous rate of a reaction. And the instantaneous rate of a reaction is much, much better because we're looking at a single data point. So another issue we have here with the average rate, going back for a second, is that we're using 2 data points. Now, these 2 data points expand this whole area of the graph. Even within this area of the graph, the rate changes. The rate up here at 5,0.27 is actually lower than the rate here at 0, 0. And so looking at an average, the issue is not just that it's going to be different from here to maybe up here, but it's actually going to be different within the span of those 2 points. So using 2 data points is not the best way to find rate. The instantaneous rate of a reaction is a much better way of finding rate. Why? Because the instantaneous rate of a reaction does not use 2 data points to find the rate. It uses a single data point. So what does it mean by instantaneous rate of reaction? We call it the instantaneous rate because it's not the average between 2 points. It is the specific rate at a single point in the reaction. So let's say we had the exact same reaction, but we're now graphing the cyclopropane versus time. So now again, the reaction was, let me write it up here. The reaction was the cyclopropane decomposes to make propene. Actually, I shouldn't say decomposes, an isomerization reaction, but it changes. So it changes to make propene, right? Meaning that the reactant is the cyclopropane, propene is a product. In the reaction we had earlier, or in the graph we had earlier, the graph has a positive slope because we're looking at the concentration of propene. But here, this graph, we are not looking at the concentration of propene. We are instead looking at the concentration of cyclopropane, which is a reactant. Because we're looking at the concentration of a reactant and not a product, we have to remember that the concentration of the reactant, so in this case the concentration of the cyclopropane, is going to decrease over time. So you can see how the other graph, which looked at propene, increased over time, the concentration. But for the cyclopropane, the concentration decreases over time. And that makes sense because we're looking at a reactant now, not a product. But the idea is the same. We're looking at cyclopropane concentration over time, so we're still looking at rate. When we're looking at a concentration versus time graph, and we want to find the instantaneous dipole, or not dipole, the instantaneous rate, what we're going to do is we're going to choose a single point. So let's say I wanted to look at the instantaneous rate at exactly 10 minutes. I'm going to use one single point to do this. So I'm going to use that 10-minute point right here. Oops, right. Come on. Right here. So I'm just going to use this point. Unlike the other method, the average method, this uses 1 point instead of 2. Now what I'm going to do is I'm going to choose that point that I'm trying to get the instantaneous rate for, and I'm going to draw what we call a tangent line. The tangent line is this line right here. Pardon me while I probably butcher this, but this line right here, which touches the point at a single place. So a tangent line by definition, and the tangent line, we draw it, we'll call it tangent line, this is how we spell that. The tangent line only touches the graph at one singular point. That one singular point being that 10-minute mark that we are looking at. So we're going to draw a tangent line. And then what we're going to do is, instead of measuring 2 points on the graph, which is not linear, we're going to choose 2 points on the tangent line, which is linear, and use those to look at the rate. Because remember, the rate is the slope of the graph. The tangent line should have the same slope as the graph does at that one particular point. So instead of using 2 points on the graph itself, which is not linear, we're going to use 2 points on the tangent line of the graph to figure out the rate of the reaction at that particular point. That's why we call this an instantaneous rate, because it is the rate particularly, specifically at that one point in time, instead of over the average chunk of the graph itself. We're usually going to use this method when it comes to calculating rates, because this method is much more accurate as it looks at a single point. More specifically, we're usually going to use this method, but instead of using it for like time 10 minutes or 20 minutes, we're going to use this method at time 0. We call this the initial rate of the reaction. By looking at time 0, we get the rate of the reaction at the very beginning of the reaction. Now, one of the things that you might be wondering is, how the heck am I supposed to draw a tangent line, right? Now, that is usually what daunts most students. We don't need to worry too much about your tangent line being perfect. You're going to choose a point, and you're going to draw a line that looks like it should be the tangent line, that it only touches the graph at that one point. And then if it's a little skewed, if it's not ideal or exactly where it's supposed to be, we're not going to worry about that, because what you're getting graded on is not the drawing on the tangent line, but of the using of the tangent line. So as long as your tangent line looks like it could be a tangent line, it's only touching the graph in one place. It doesn't need to be perfect, because what you're judged on is not how perfect your tangent line is, but actually drawing a tangent line and then using it, how you use it. Not the specifics of, is your tangent line perfect? So let's look at how we do this. So we have this graph, right? This graph is going to be the cyclopropane concentration versus time. So it's the exact same graph we're just looking at. So what are the steps to figuring out the rate of this reaction? Well, first we're going to choose the point in the graph that we want the rate for. In this example, we're going to use 10 minutes, this point right here. But again, most of the time we will use the initial rate, which is going to be that tangent line, but for time 0, meaning the very first point on your graph. But let's look at this one just because we have the graph here and we've been looking at this graph. So what we're going to do is we're going to choose that point, and we're going to we're going to draw a tangent line that touches that point just once. Again, the tangent line doesn't need to be perfect. What you're looking for is that the two angles between the line and the curve should be very similar, meaning that the angle that forms right here and the angle that forms right here should be very similar, and that line should only be touching this once. The other angles that you can look at are the angles that it makes with the x and y axis. So if you're looking at your tangent line, you're looking for very similar angles when it comes to the x-axis and your tangent line. But again, the actual definition of a tangent line will be one where this angle right here, let me do no yellow, where this angle right here and this angle right here are very similar. All right. So this is a fairly good tangent line. It doesn't need to be perfect. Again, you're not getting graded on how perfect your tangent line is. So we're going to draw a tangent line on that point. Obviously, if we're choosing an initial rate, we will use this point up here, and then we'll make a tangent line there. But once you draw your tangent line, you're going to extend the tangent line all the way to the x and y axis. And you're going to see where that tangent line touches the x and y axis. So in this particular case, my tangent line on the x-axis goes all the way to the y-axis goes all the way to 1.4. And on the x-axis, it goes all the way to 35. So those are going to be the two coordinates we work with. On the x-axis, it touches at 1.4, meaning the coordinates are going to be 0, 1.4, because if you remember, again, from math, and hopefully you do, the x-axis or the x-coordinate is the first one, the y-coordinate is the second one, same thing here, x, y. So we have 0, 1.4, and then on the x-axis we have 35, which is the x-intercept, 0, because y is 0 here. We're then going to use those 2 points in order to calculate the slope of this tangent line. Remember, slope is just rise over run. So we're going to do the difference in the y-coordinates minus the difference in the x-coordinates, keeping in mind which one's x2 and y2 and which is x1 and y1. So here, y2, if we make the blue one y2, that's going to be 0. And x2, y1 is going to be 1.4. And then x2 is going to be 35. And x1 is going to be 0. So we do 0 minus 1.4 over 35 minus 0. That's negative 1.4 over 35. Or, roughly, negative 6.67 times 10 to the negative 4 moles per cubic decimeter per second. Again, this is always going to be the units for rate. These units don't change. So this is the rate. This is the instantaneous slope, the instantaneous rate at this one particular point at 10 minutes. That means that at that one particular point at 10 minutes, the concentration of cyclopropane was changing by 6.67 times 10 to the negative 4 moles per cubic decimeter for every second the reaction was allowed to proceed. Now this makes sense. Why? This makes sense because this number is negative. If we remember, we're talking here about a reactant rate. The reactants are going to be used up over time, meaning that the rate has to be negative because their concentration is decreasing over time. And because the rate is equal to the slope of the line, a graph where the concentration decreases over time, where the y-axis decreases over time, has to have a negative slope. So the reactant rate at that particular point is going to be negative. If we had done this for the concentration graph at the exact same point in time, we will get the exact same rate, but it will be positive because the product concentration is increasing over time. That of propene is increasing instead of decreasing. But because we're doing this for a reactant, cyclopropane, that concentration is going to decrease over time. So that's how we use the slope of a tangent line on the graph to calculate the instantaneous rate at a particular point in time. Again, that particular point in time, usually, unless the questions tell you otherwise, you would be using the initial rate, which is going to be that tangent line being drawn for the very beginning of that graph. So now that we know how to calculate the instantaneous rates, which again is going to be the ones that are more commonly used, let's look at how those instantaneous rates can change over the course of the reaction. If we measure the rate of a reaction, the instantaneous rate of a reaction, as it proceeds at different points, we can see that the rate of the reaction is going to decrease. So if we look at this graph right here, this is a graph we were working with before. We have the cyclopropane versus concentration versus time graph. So this is the exact same graph we were looking at earlier. But now we have done the tangents at a bunch of different points. So we have the initial rate of the reaction, which is this first tangent right here at time 0. We have the instantaneous rate of the reaction at this point, which we're working with before, which is 10 minutes. And then we have another rate of reaction here for something, I believe this is something around 28 minutes. So we have another tangent line here. So we have tangent lines, and let me use a color that's gonna pop here. We have tangent line 1 up here, which is for the initial rate at time 0. We have this tangent line right here, which is for time 10 minutes. And we have this tangent line right here, which is at time roughly 28 minutes. So as we can see, we have tangent line 1, tangent line 2, and tangent line 3. So I'm going to mark where they end. So this is 1, 2, and 3. So what we can see here is that as the reaction proceeds from 0 minutes to 10 minutes to 28 minutes, the rate of the reaction is going to decrease. The rate at initial, this line right here, has a much higher, much steeper slope than the rate of the reaction at 28 minutes, which has a much more horizontal line, a much lower slope, a much slower rate. So we can physically see with the slopes of these tangent lines how the rate of the reaction slows down as the reaction proceeds. That's because the rate of a reaction is going to be dependent on the reactant concentration. And as the reaction goes on, the concentration of the reactant, as we can physically see on this graph, decreases. The cyclopropane is our reactant, and we can see in this graph, the non-dashed graph, that the reactant concentration goes down and down and down. Because the reactant concentration goes down, so does the rate of the reaction. By graphing the reaction rate versus the concentration of the reactants, at the point in which we can see the direct correlation between the two. So this is a different graph, and you got to be very careful with the y and x axis and their labeling. This graph we were looking at earlier is a cyclopropane concentration versus time graph. So concentration of reactant versus time. The slope of that line is the rate. This right here is a rate of decrease of cyclopropane, meaning the rate of this reaction according to cyclopropane versus the concentration of cyclopropane. So we can see in this graph that as the concentration of cyclopropane is higher, so is the rate of the reaction, which is on the y-axis. So when the concentration of cyclopropane is 1.5, which is the very beginning of the reaction, the rate is high. It's 1 times 10 to the negative 3, which is what this is right here. When that concentration drops down to 1, which is the concentration that it reaches at time 10 minutes, the rate of the reaction has slowed down to around 6.67 times 10 to the negative 4. Then when the concentration reaches around 0.5, which is at 28 minutes, the rate has farther slowed down to around 3.30 times 10 to the negative 4. So the less concentration of the reactant we have, the lower the rate of the reaction is. So we can literally see here the direct correlation between concentration of reactant and rate of the reaction. The higher the concentration of the reactant, the higher the rate of the reaction is, as seen by this graph. So this graph shows us that direct correlation between concentration of reactant and and rate. So let's see why this happens. What explains the reasoning behind this is something we call the collision theory. Collision theory is something that we briefly mentioned and talked about when we discussed gases earlier in chapter, I believe it was chapter 4. We can use collision theory to explain the effects of concentration of the reactants, temperature, and the surface area of a reaction on the rate of a reaction. Collision theory is actually very simple. It explains the conditions that are necessary for particles of the reactants to have a successful reaction. And there are two main factors that are going to affect whether two reactant particles will actually react when they crash into each other. The first is their orientation. So in which way are the particles oriented? And the second is their energy. So when particles collide, what the collision theory says is that they have to do two things in order to actually react. First, they have to collide with enough energy to break the bonds that are needed for the reaction to occur. So essentially, let's say we have the reaction of hydrogen gas and chlorine gas crashing into each other to make hydrogen chloride gas. So H2 plus Cl2 making 2 HCl molecules. So what collision theory says is that if hydrogen crashes into chlorine, but they don't have enough energy to break the bonds between the hydrogen and the chlorine, that the particles are simply going to just bounce off each other. They're not going to react with each other. Because when they collide, they need to have enough energy to break those bonds. If they collide and they do have enough energy, so they're moving very fast, which is symbolized here by these big arrows, then what's going to happen when they collide with each other is that these bonds are going to be broken, and new bonds will form between the hydrogen and the chlorine on the molecules, creating our products, the two HCl molecules. That's what collision theory says. When two molecules collide, they have to have enough energy to essentially overcome, to use a word from earlier from kinetics, not from kinetics, from equilibrium and from thermodynamics, they need to collide to enough energy to overcome the activation energy. And that activation energy is the energy needed to break these bonds. Now, colliding particles have to collide not only with enough energy, but also with the right orientation. So colliding particles have to collide with the appropriate orientation to react for the new bonds to form. That means that when these two particles collide, they need to do so that the hydrogen and the chlorines that are going to make these new particles are next to each other when they collide. Because if they collided end to end instead of side to side like this, then one of the chlorines and one of the hydrogens wouldn't have anything to react with after the collision, and so the reaction wouldn't happen. So the collision has to have enough energy, and it has to be oriented in the right direction, the right orientation, in order for the particles to collide and actually react. We call the collision that meets both criteria, a collision that has enough energy and is in the appropriate orientation, a successful collision, or sometimes called an effective collision. So an effective collision or a successful collision is one where the particles crash with the right orientation and with enough energy to create a reaction. While those that fail one or both of the criteria are called ineffective or unsuccessful collisions. All right. This collision theory is what essentially explains kinetics. And we're going to go into the details in the next two sections where we're going to look at how concentration affects the rate of a reaction in section 2 and how temperature affects the rate of reaction in section 3. But they were going to use this collision theory to explain how both of those happen. Well, that is it for this section. Thank you for watching, and I'll see you in the next video.